my name is Corel and I'm here to introduce you to our team, Jediodes. So our game is a Star Wars themed game in which we have created this lightsaber that's very interactive, in which we choose different gummy bears to choose the color of our lightsaber. And the way we are trying to solve the creativity deficit is to use this very advanced lightsaber to fight the alien invasion. So our system has a bunch of different sensors that provide user feedback, and one of them is a speaker. I'm gonna plug it in right now. So this speaker has a lot of different sounds, as well as the theme sound of our game and different sound effect of our lightsaber. It uses a different frequency array that contains the melody and the duration of each melody, and it's sent into our system into a PWM signal.
In terms of the mechanical system for our project, it's split up into two big parts. One is the lightsaber, another is the target board and the timing clock flipboard system. For the lightsaber, it's composed of 5 different sections. One is the blade portion that has a translucent tubing that's about 1 meter long. And for the hilt, it's made up of 4 different sections inspired by Anakin Skywalker's hilt. At the topmost section, it holds a button that sends external interrupt to move between different stages of the game. It also has a speaker for different sound effects. In the second compartment, there are 2 vibration motors that take just a regular output to give haptic feedback to the users so they know when to swing. At the bottom, there is also an IMU to detect whether or not the user swung in the right direction or not. Below that is the LED chamber that has a gummy bear detection circuit that we also use for lab. But the different thing about this circuit is that instead of using shift registers, we have implemented analog read for the phototransistors. So it reads the value of the refracted light from a scale from 0 to 100, and we basically do different thresholding to determine the color. At the bottom, we hold various wires that are routed through, as well as this I2C extender that will send signals through a very long distance so we can accurately read all of our signals. So just like the gummy bear detector circuit we did in lab, this works in a similar fashion. But in idle phase, essentially the user will choose a gummy bear, put it inside, and put this cover, which is also inspired by the Star Wars movie. But what will happen is, like in the labs, the LEDs will turn in sequence and send signals to the phototransistor below, which we are reading through analog and convert to a 0 to 100 scale and threshold to find the right color. So if you want to see them turning in sequence, it's like.
So in the hilt of this saber, we have MPU 6050, which is a 6-axis IMU, 3 axis of gyro and 3 of accelerometer. We communicate with the MPU with the I2C protocol, which we have implemented. And to make this process non-blocking, we implemented a DMA. So all the data goes to the DMA buffer, which processes it in parallel while all the other processes are going on. For detecting the swing, we just get a recent window and we integrate our gyro and acceleration values in that window. From that, we check if the motion is big enough and in a certain direction, and we classify it as a swing, which is then compared with the ground truth, which gives us a correct or incorrect value for the game.
So the lighting effects on our lightsaber are produced using 2 NeoPixel LED strips. Each strip consists of 144 LEDs, and they are controlled using PWM signals. The lighting effects that this strip can produce include the saber turning on, the saber turning off, as well as the saber toggling during the game or during celebrations.
So for the interface part, we have like 2 models doing like the clock flipboard style information. So the first one is this, which is like the one that show the directionality of the swing the user need to input to compare with the IMU if the swing is correct or not. So you can see like there's like multiple phases on this model. There's like the status display, whether player is win or lost. This win, it is lost, it is a welcome, and then like the swing direction that we use in game. So there would be like 4 direction, up, down, left, and right, all with different art style, as you can see. Yes. And for the second model display is for the time dial to see how many seconds left in game. This count from like 6 to 0 in 5-second incremental. Yeah. So for both of these models, we intend to use closed loop control to measure the exact angle is turned. But however, the encoder might not work on the bigger one, so we improvise the plan and do the open loop by time-based flipping instead.
Now I'm going to talk about the game state machine. So the game starts with the state machine in the idle state, where the bottom 2 LEDs of the LED strip are glowing and intro welcoming music is being played. Now on pressing the button, the state machine can go to the saber initialized state, where 4 LEDs, which are part of a gummy bear color detection circuit, turn on one by one. And if the gummy bear color is detected, then the state machine transitions to the saber turn on state, and if the gummy bear is undetected, then the state machine goes back to the idle state. Now, in the saber turn on state, every single LED of the LED strip turns on one by one, and at the same time, background music of the lightsaber turning on is played. Now, once every single LED of the LED strip is on, the state machine goes to the saber ready state, and the game can begin on the press of a button. However, if the user does not press a button for 10 seconds, the state machine transitions back to the idle state. Now, once the user presses the button, the game begins, and each round of the game lasts 5 seconds. And there are 6 such rounds. So, at the start of each round, the motor showing flipboard direction flips, and the timer as well indicates that the 5-second interval has begun. And 2.5 seconds into each 5-second interval, the vibration motor in the hilt of the lightsaber vibrates, indicating that the user must start swinging. And this is marked by a transition to the in-game pairing state, and during this state, the IMU swing detection algorithm is active. Now, in each round, the state machine stays in the in-game pairing state for 1 second, and at the end of this 1-second interval, the detected swing is compared with a ground truth, and if the swing direction is correct, then the lightsaber turns white for a fraction of a second, and if the swing direction is wrong, the lightsaber turns red for a fraction of a second. Now, during the game, the in-game music is constantly played, and once the game is done, the state machine transitions to the end of game state. In the end of game state, the user is notified of whether they won the game or lost. If they win the game, then the lightsaber blinks in the color that was originally present, and victory music is played. And if the player loses the game, the lightsaber turns red and blinks in the red color, and loss music is played. After a 10-second duration, the end of game state, the state machine goes to the saber turn off state, which is the exact opposite of the saber turn on state, and every single LED of the LED strip turns off while music of the lightsaber turning off is played. From this state, the state machine transitions back to the idle state so that the game can be played again.
Welcome state.